Hello, everyone. Now, another very exciting course material, which is data and signal spread spectrum technology, will be discussed today. Okay, so um, basically, spread spectrum is the following. Has been developed in World War II by military and now widely used for wireless LAN. Um, and, and having spread spectrum um, will have a very low probability of intercept and anti-jam, which is really good. That's what we have these days, right? Um, rather than using narrow band, the one that we are using is a wider frequency band. So what it does is that rather than using a wide and very peak signal, if our frequency band is this wide, then we press this down and spread the whole signal throughout all this frequency band. In order to do that, we use uh, uh, pseudo random number. Okay, it is not really the pseudo random number, but it looks like. So I wanted to read uh, the slides, but I'm going to give you my lecture. Remember that I want to keep my video lecture shorter. Some people do not like the longer video lecture, so make it short. So what we are using is that exclusive OR operator. Those who do not have clear confidence on exclusive OR, you need to check out one of my lecture. So I explained it there very clearly. Let's say this is a chip sequence, chipping sequence. So this is two chip sets in a sequence. This is, let me see how I can do, because my mouse movement is not really clearly shown. So what I'm going to do, let me see if I can get any, maybe this, right? So this is, I think this is one chip seconds. Let me see, chip sequence. Make it wider, okay, lighter. So this is one, and this is a second chip sets. Okay, so okay, the size of this chip sequence is, so as you can see, if I plug that here, then 1, 2, 3, 4, 5, 6, 7 bits, right? And another 7 bits. But data sets that we have is 1 bit. So we're actually 1 bit of each. So we have total 2 bits. So these bits will be transferred over this, say, chipping sequence. Okay. Then how can we make it? So for that, we use exclusive OR operator. Um, and having that, if we have this kind of data sets, so 0, 1, 0, 0, then for example, if I expand that, then this data is, this is pseudo number bit stream. We call that chip sequence, this chipping sequence, and this data is exclusive OR operator applied. Therefore, the data will be like this. Okay, 0 and 1, 0, 1, 1. It's 1, 0. 0, 1, 1, 0. So it'll be 0, 1, 1, 0, maybe here. It's not really clearly lined up, but if we come here, then we see it, right? 0, 1, 1, 0, and then 0 are exclusive OR. So 0 will be spread out. So it's not just a single 0, but maybe to make this the identical size, and we need to have a 0, 0, 0, 0. So 4 zeros and 4 bits of chipping sequence. Then we have exclusive OR over those. And 0 exclusive OR 0 means 0. 0 exclusive 1 means 1. 0 exclusive 1 is 1. 0 exclusive 0 is 0. So we have a 0, 1, 1, 0. This is the spread spectrum. Okay. When we have that spread spectrum at the receiver side, and we apply the same pseudo number, chipping sequence, to apply exclusive OR, then we will get the original ones back, right? So that's what it is. So let me jump. The question here is that how can we choose pseudo-random number? It depends on the pseudo-random number. This is not only one data sequence. The idea here is that what if we have so many senders to send the data? So we want to collect all of those and make a one signal, which is a spread spectrum. So one spread spectrum signal is transmitted. So at the receiver side, where there are multiple receivers, so first receiver can receive the same message that is sent by sender one. Second receiver will receive the same data as transmitted by sender 2, and so on and so forth. So here we modulate at the transmitter side. At the receiver side, we have to demodulate it. How can we split them? Those things needs to be, that depends on the set of this pseudo-random number. This chipping sequence is not the same among the senders, among the receivers. They only have the same chipping sequence between a pair, sender and receiver. So different pair, different sender and receivers may use different chipping sequence. In that way, it can be split. It can be combined and split, and therefore the original data can be restored. If we mix them, then we cannot make it accurately. So how can you make that? To do that, chipping sequence, it needs to be here. Chipping sequence needs to be orthogonal. They need to be orthogonal. Okay, what does that mean? Orthogonal. Orthogonal means in mathematics, dot product should be 0. Pictorially, if we choose 1, 1 and 1 minus 1, of course they are orthogonal, right? One signal goes to northeast and another signal goes to southeast. Then they are orthogonal directions, two different directions. If they are completely orthogonal, so 90 degree, then there is no interference because they are different phase. Okay, as I said here, if scalar product is 0, which means the dot product is 0, then it means there is no interference. What do you mean by scalar production? Scalar production here is that if we have a 1, 1 and 1 minus 1, as we can see here, okay, here. If we do scalar products, we products vertically, 1 times 1 is 1. And the next column, 1 times minus 1 is minus 1. We add them. 1 minus 1 equals 0. So actually, 0. Dot product is 0. Therefore, we know there is no interference. What is the principles of wireless communication? If there is no interference among themselves, then we receive the data as it was sent, right? As it was sent. So that is the idea. Let's say, therefore, 1, 1 and 1 minus 1, they are orthogonal. So pair of 1, 1 and 1 minus 1, that is orthogonal. If we spread, given one data item, if we spread it into 2, then we can use this. If we use this, then this is one chipping sequence, this is another chipping sequence. So only 2 chipping sequences available, which means we can serve 2 senders. What if we want to serve 4 senders? So first sender will have 1, 1, 1, 1. Rectangle. So 1, 1, 1, 1. Right? Okay. 1, 1, 1, 1. And second sender will have for the chipping sequence 1 minus 1, 1 minus 1. And third one's 1, 1, minus 1, minus 1. And fourth message will have the chipping sequence 1, minus 1, minus 1, and 1. They are all orthogonal. How can we make orthogonal? Say this is orthogonal. Then we can copy it to its right hand side, and we can copy it to the lower. So we copied 2 right and 2 lower. And then in this diagonal direction, we invert it. 1, 1, 1 minus 1 can be inverted into minus 1, minus 1, minus 1, right? This and these 2 are inverted. And these 3 are copied, they are identical. In this way, all of these 4 can be orthogonal. If you choose any 2 of these, they're also orthogonal. Vertically, you make dot products. 1 times 1 is a 1. 1 minus 1 minus 1. So 1 minus 1 is a 0. 1 and 1 minus 1 is 0. So totally, if we apply this thing there, and that is also 0. If we choose only 3 senders, still possible, right? So 1, 1, 1, that is 1, and minus 1, minus 1, and 1. Therefore, that is 0. If we choose all 4, still that is 0, right? So this works very well, right? So having that, we can apply that here. We have a message in digital, and chipping sequence is like a signal, so it has high voltage and low voltages. Let's say high voltage 1, a low voltage minus 1, right? So this high voltage and low voltage needs to be converted to digital data. Therefore, we can do exclusive OR, right? This high voltage and low voltage cannot be applied to that. So next slide shows to you how can we convert. The high voltage in signal will be 0 in digital data, and low voltage will be 1. And in reverse way, if we have the digital signal 0, digital data 0, then it'll be high voltage 1. Digital signal 1, then that will be low voltage, which is minus 1. It's not really 1 and minus 1. It could be any maybe 2 voltages or 5 voltages, 10 voltages. It depends, right? Depends on the amount of energy that you want to use. Therefore, it is proportional to the distance that signal may reach. So, so it is converted. So 1 minus 1, 1 minus 1, 1 minus 1 in the chipping sequence or the signal voltages can be, say that is 1 will be 0, and minus 1 will be 1. Therefore, we have these many sequences. Okay, and we have 2 data items, 0 and 0. So the first chipping sequence, we copy the zeros all, and second chipping sequence, we also copy the second 0 all, and then we apply exclusive OR. Then it'll be 0, 1, 0, 1, 0, 1, right? Same thing, 0, 1, 0, 1. Okay, and second sender will send the message 1, 0. It has 1, 1 minus 1, 1 minus 1 minus 1. This is independent but orthogonal to the previous chipping sequence. So it is converted to data, digital data. So 0, 0, 1, 1. We applied the exclusive OR operator. Same thing for the third sender. Okay, third sender use different chipping sequence. Therefore, we have different digits in binary and also different data sets and exclusive OR. Once, so having this 4 digits of 4 digits of chipping sequence. So each digit is a binary 1 or 0. Therefore, we have only 4 distinct chipping sequence, which means maximally we may have 4 senders. And if we have 8 senders maximum, then we need to double this. Okay. So having those 4 the the result of the exclusive OR operations. Then this is data, then we need to convert it back to the voltages, right? This is from here, there. So if it is a 0, then that is 1. If it is 1, that will be -1. This will be -1. So we add them all. So 1 minus 1 minus 1 means -1, right? If it is a 1, then -1, -1, -1. So that'll be -3. So we add bitwise. So each bit in this slide, maybe column wise. So this is 1, this is 1, this is -1, then it'll be 1 if we add them all. So we have this voltages. That voltage is nothing but this. So this is the voltage that we obtained. So this. So what happens is, so far, we have 3 senders. Each sender has a different message to send. We collect them all and send one signal. This is one signal. This is spread spectrum signal. That spread spectrum signal is nothing but this in voltages, right? And the next slide is that how can we decode it? So this up to this, it's not really encoded, but this is modulated, right? How can you demodulate it? Demodulate it in this way. This is the signal that we receive, okay? And then the chip sequence that the user one uses is 1 minus 1, 1 minus 1. So go back to here. So chip sequence is 1 minus 1, 1 minus 1. So that is a shared a pair of sender and receiver. So 1 minus 1 here and also there, we apply that throughout all signals. So every 4 data, we have one restored data back, right? So how can we bring back 0, 0? Again, this is bitwise multiplication. So -1 times 1, then that is -1. Okay, so -1 times -1, that is 3. And then third bits, 1 times 1 equal 1. And fourth bits, -1 times -1 is 1. So we add this 4 data, then there will be 4. What is the average? Average is 4 over 4. So number is 0. Okay. Same thing, second one is 0. So this is 0, 0. That is a message received by receiver 1. This message can be obtained only by receiver 1 because receiver 1 and the sender 1 shared the same chipping sequence. Receiver 2, because it has a different chipping sequence, may have different data sets. Demodulated, right? 1, 0. So this is the one that you need to do. And then there is an exercise that you need to do. Yeah, this is an exercise that is available on the website. And then the final question is that the one that we used here is digital only. Can you do that, for example, modulation and demodulation and analog? Yes, that is also possible, right? But this is more sinusoidal type of format. But idea is pretty much the same, right? This is like a GPX sequence. This is the data. We spread this data over the GPX sequence so that we have this kind of data. And then that one spread spectrum signal is transmitted. And then at the receiver side, and multiple different receivers can receive the data designated to that specific receiver. Okay. Right. This is a short explanation, and then there is a exciting lab work and also homework number 2 that is on Blackboard. Right. Thank you.